Hey there, everybody. Welcome back. This will be our final video. This is on non-dimensionalization. It is not in the calculus textbooks. It's something interesting from fluid dynamics. I studied in grad school, and it's upper end. And I've shown you equations before, like, for example, the Navier-Stokes equations. I've shown this from NASA in class before. There's a lot of like terms here, the Reynolds number, the Prandtl number. You know, what are these things? Where do they come from? So that's what we're here to talk about, and give you a little information on where stuff's coming from. So let me get my slides back up. There we go. So what we want to do, we're going to start with the basic Navier-Stokes equations, or at least we're going to look at the conservation of momentum, I believe. And we're gonna, what it does is there's a lot of parameters going on, things that that really just clog up the system. We've got velocity. Let's bring it back up to show real quick. We've got U is velocity. We've got let's see. P is for there's pressure in here. We've got gravity in here. We've got this tensor thing. You're like, what is this T thing? The stress tensor. So there's different things going on. Everything has its units. And so what we want to kind of do is, like, depending on who we're talking with, the units in SI units is different than our units, American units. So let's get rid of them. Let's gather them all in one spot and address them. So non-dimensionalization partially or fully removes those dimensions from an equation. And you'll see what happens. They end up clustering in one or two areas. So let's take a look at what's going on. It might help us give it a better understanding of physical situations when we do it. So the incompressible Navier-Stokes equation, like I was saying, for momentum is rho times the time derivative of velocity plus the velocity dotted with the gradient. Then we're going to multiply that by the velocity again. Then that's just the left-hand side. The right-hand side is the negative gradient of the pressure, plus mu times the Laplacian of the velocity vector again, plus rho times, these are just, G represents external forces. It could just be gravity, but it could be anything. And I wrote U, but this is actually needs to be done in each direction. We need the X components, we need the Y components. It breaks it down into each one. Okay. Let's see. Do I want this one yet? Yeah, there we go. This is another way of seeing. This is a better way of seeing it. So we're going in the X direction. Mu or U is going to be our speed in the U direct or the X direction. And then we have V for Y direction and W for the Z direction. You'll notice that Laplacian, the vector on top stays the same, but each one of these, the thing is different. So we end up addressing that. This breaks into three different equations. Okay. So what does each term mean here? Rho is density. P is pressure. U is our flow, our velocity vector. And G is our external field, which can be gravity, is usually gravity, but there could be other things. I also have a mu in here. Mu is dynamic viscosity. Dynamic viscosity measures resistance to deformation by shear flow. What I mean by shear flow is if I have like a surface here and wind is blowing across the top, how much is that wind getting this stuff to move on the top? Okay, on a solid, it doesn't do shit. Just slides right over. The wind blows over and doesn't do nothing. On something like water, it'll push the waves and make waves. Jello, it doesn't really, you know, if the wind's strong enough, it could move the Jello. Like cause it to deform, but generally not so. So we give this variable here, dynamic viscosity, measures how much we resist that change. So Jello has high resistance where water does not. So thick fluids like Jello or, you know, cream or something like that. Cream is not anywhere near as thick as Jello, but it's thicker than water. They have a higher, the more thick it is, the higher the mu is. We use mu in mathematics. Sometimes chemists and physicists use eta instead of mu. And the main idea is to divide out the units of measurement. And we're going to do that by using a capital variable, as we'll see in a second. See if there's anything else I wanted to show you from the slides. This one, this entire sequence, this slideshow sequence that I'm looking at, it's 75 things long. It's pretty good on setting it up. But I wanted to show this one here. And that's why they have G of X, G of Y, G of Z, because it's not necessarily gravity just going downwards as we're used to. And when we do those things, when we're taking that gradient, we get these weird values where, like, we've got Vxx and Vxy and Vxz. We're doing that gradient. We get some weird stuff going on. So they have a tensor. It's called the stress tensor. It's beyond the scope of doing this in a short video. But there's a lot of stuff going on. So we're just only unpacking a little bit of it. Okay. I think that's the best one to use right now. That'll be it for this video. Actually, one more thing. We have this part right here, this du dt. So the time derivative of velocity, and then our velocity components times the gradient of the velocity in a particular direction. This all gets abbreviated into one other thing. They often call it big du dt. And big du dt, it is this right here. Let's see, do I have a pencil? Yeah. So big du dt breaks down into this right here. And so sometimes you'll see this, you'll see du dt like that, rather than this, and that's what they're showing. Okay, that'll be it for this video. Peace.